We flip a switch, plug in our phones, and boom, electricity's there like magic. In this episode, we'll dive into the fascinating world of electricity, what it actually is, how it travels to your home, and why it's such an essential part of modern life. We'll also answer questions you've probably always wondered about, like how does flipping a switch turn on your light? And what happens to all that electricity when you aren't using it? All right, let's start with the basics. Electricity is the flow of electrons, those tiny charged particles that whiz around atoms. Picture electrons as little runners, sprinting down a racetrack. That racetrack is a conductor, like a copper wire, which allows the electrons to flow from one point to another. This movement is what creates electric current. But how exactly does this flow of electrons power things? Imagine a water pipe. Water represents the electrons, and the pipe is the conductor, or wire. The pressure pushing the water through the pipe is like voltage. The speed or flow of the water itself is the current, and the overall power, the ability to do work, is measured in wattage. Voltage, current, and wattage are all related. Power equals voltage times current. More pressure, that is more voltage, or faster water, that is more current, equals more power. Now, when electricity flows into a device, the electrons cause components inside to move or heat up. For example, in a light bulb, the movement of electrons makes the filament glow, producing light. In your smartphone, it powers circuits that turn on your screen and let you interact with your apps. In essence, flowing electrons carry energy that gets turned into something useful: light, heat, or motion. There are two main kinds of electricity: static and current. Static electricity happens when electrons build up on an object, waiting for the chance to jump, like when you rub a balloon on your hair and make it stand up. It's temporary, and the energy is released in a single zap. On the other hand, current electricity is a continuous flow of electrons, which we harness to power our homes, gadgets, and pretty much everything else. So now that we understand electricity on a small scale, how does it travel all the way from a power plant to your house? Well, let's go back to our water pipe analogy. If you're trying to move water across long distances, like from a reservoir to a distant town, you need to use bigger pipes or more pressure to avoid losing too much water on the way. With electricity, we use high-voltage transmission lines to minimize energy loss over long distances. The journey starts at a power plant, where electricity is generated. This could be from burning coal, capturing wind, or using nuclear energy. Once generated, this electricity is pumped into high-voltage lines, which carry it across large distances. The higher the voltage, the easier it is to move electricity efficiently without losing too much along the way. But here's the thing: high-voltage electricity is dangerous for regular use. So, when it gets closer to your home, it's sent to substations, which step down the voltage, making it safe to flow through your neighborhood's power lines and into your home. Electricity doesn't just sit around waiting for you to use it. It's constantly being generated and sent through the grid. But what happens when demand is low, like late at night when everyone's asleep? The grid has to balance supply and demand in real time. Power plants adjust their output depending on how much electricity is needed. During the day, when demand is high, think businesses running, people using appliances. The grid is cranking out a lot of power. But at night, when most of us are asleep, demand drops. Power plants can't just stop generating electricity entirely, so they scale down production. This is why renewable sources like wind and solar are so useful. They can easily ramp up and down based on demand, while fossil fuel plants are slower to adjust. But where does the electricity go if there's more supply than demand? In some cases, power plants may reduce output, but in others, excess energy is stored in batteries or other storage systems, which can be used later when demand spikes again. Now, AC and DC, the great rivalry of the electricity world. But what do they mean, and why does it matter? In DC, direct current, the flow of electrons is straightforward, like water running smoothly through a garden hose in one direction. This works well for short distances, but over long distances, there's a big problem: resistance. The farther the water, or electrons, has to travel, the more it slows down and loses energy as heat, kind of like friction inside the hose. With DC, you'd need thick cables or frequent boosters to keep the energy flowing without major losses, which isn't practical for long-distance transmission. Now let's dive into AC, alternating current. Instead of flowing in one direction like a constant stream of water, AC is more like a rapid back and forth sloshing motion in the pipe. This sloshing is created by the alternator, a device that spins magnets to generate a constantly changing magnetic field, which forces the electrons to keep reversing direction many times per second. But why does this back and forth sloshing help with long-distance travel? Here's the trick. AC allows us to easily change the voltage using devices called transformers. By increasing the voltage to very high levels, think hundreds of thousands of volts, and lowering the current, AC can travel long distances with minimal energy loss. This is because energy loss due to resistance depends on current. So, when you use AC to step up the voltage, you're stepping down the current, which means much less energy is wasted as heat in the wires. Imagine sending a strong pulse of water through a very narrow pipe. Less water is wasted along the way, and it arrives at its destination more efficiently. That's what AC does. Once the electricity reaches its destination, transformers again come into play, lowering the voltage so it's safe to use in homes and businesses. In DC, this type of voltage transformation isn't nearly as easy. In summary, AC's ability to alternate and work with transformers means it can be transmitted over long distances without losing much energy, unlike DC, which would lose a lot more energy along the way. This makes AC ideal for the power grid, while DC is still used for small-scale things like batteries. Let's talk about one of nature's coolest electric generators, the electric eel. These fascinating creatures can produce a shocking amount of electricity, up to 600 volts in a single zap. But how does the electric eel do it? The secret lies in special cells called electrocytes. Think of these cells as tiny biological batteries. Normally, they're inactive, but when the eel wants to generate electricity, it activates them. These cells are stacked up like the cells in a battery, and when they're all triggered at once, they create an electric current. This current flows through the water and can be used to stun prey or defend against predators. It's like nature's very own taser. Fun fact, electric eels don't just use their electricity for defense or attack, they can also emit low-voltage pulses to sense their environment, kind of like biological radar. Electricity is one of those things we take for granted, but when you break it down, it's truly fascinating. From the movement of electrons inside your devices to the massive grid that carries power across continents, it's a complex system that powers our world, often in the blink of an eye. So, the next time you plug in your phone or flip a switch, remember that you're tapping into a network of high-voltage lines, spinning turbines and whizzing electrons, all working together to keep your life running smoothly. Thanks for tuning in, and until next time, stay curious.